In the previous lessons, we used the coin analogy to understand qubits. Now we will look at the mathematics behind that idea. Do not worry. The math is not here to make things harder. It is here to describe exactly how the quantum coin moves. In quantum computing, the state of one qubit is usually written like this. This symbol, ket psi, means the current state of the qubit. It is made from two basic states, ket 0 and ket 1. The numbers alpha and beta are called amplitudes. They tell us how much of 0 and how much of 1 exists in the state. But amplitudes are not exactly probabilities. To get probabilities, we take the square of their size. The probability of measuring 0 is the size of alpha squared. The probability of measuring 1 is the size of beta squared. Because the qubit must give some result when we measure it, the probabilities must add up to 1. So the most important rule is alpha squared plus beta squared equals 1. For example, if 0 has probability 80% and 1 has probability 20%, the total is still 100%. This rule keeps the state valid. It means the qubit is always somewhere inside the allowed quantum space. Now let's write the basic states as vectors. Ket 0 is 1, 0, and ket 1 is 0, 1. So the general state of a qubit can also be written as a vector, with alpha on top and beta on the bottom. This is why we say a quantum state is a vector. Gates will act on this vector, and change it. But here is the special part. Alpha and beta are not only normal numbers, they can be complex numbers. A complex number can be imagined as an arrow on a flat plane. It has a length and an angle. The length helps us get the probability. The angle gives us phase. For example, multiplying by I rotates a complex number by 90 degrees. More generally, multiplying by e to the I phi rotates the number by an angle phi. This is why complex numbers are useful. They allow the qubit to have direction, not only size. They are essential for quantum computing. Two amplitudes can have the same probability but different phase. That difference can change what happens after gates. This connects to the idea of the Bloch sphere. The state of one qubit can be drawn as a point on a sphere. The top of the sphere represents ket 0. The bottom represents ket 1. The equator represents balanced superpositions, where 0 and 1 have equal probability. The vertical position controls the probabilities. The rotation around the sphere controls the phase. Mathematically, we can write one qubit state like this. Theta controls how close we are to 0 or 1. Phi controls the phase direction around the sphere. So yes, the probability rule gives us a sphere-like idea. But more accurately, the Bloch sphere appears because of normalization plus phase. A global rotation of both amplitudes does not change what we measure. What matters is the relative phase between them. That relative phase is what quantum gates can use later to create interference. Now let's move from one qubit to many qubits. One qubit has two basis states, 0 and 1. Two qubits have four basis states, 0, 0, 0, 1, 1, 0, 1, 0, and 1, 1. So the state of two qubits can be a combination of all four possibilities. Each possibility has its own amplitude. And again, the squared sizes of all amplitudes must add to 1. This means two qubits do not store just two values. Mathematically, their state is spread across four basis states. For 3 qubits, we have 8 basis states. For 4 qubits, 16. In general, n qubits have 2 to the n basis states. The general equation for many qubits looks like this. Here, x represents every possible bit string, 0, 0, 0, 0, 0, 1, 0, 10, 0, and so on. And the rule is still the same. All probability values must add up to 1. This is the mathematical reason quantum states become very large very quickly. But remember, this does not mean we can simply read all values at once. Measurement still gives one final result. To combine qubits mathematically, we use something called the tensor product. The tensor product is the rule for building a bigger quantum state from smaller quantum states. For example, ket0 tensor ket1 becomes ket01. Using the coin analogy, this means the first coin is in state 0 and the second coin is in state 1. As vectors, ket0 is 1, 0 and ket1 is 0, 1. Their tensor product becomes a four-dimensional vector representing the two-qubit state 0, 1. Tensor products also work with superposition. For example, ket plus tensor ket0 becomes a superposition of 0, 0 and 1, 0. This means the first qubit is in superposition while the second qubit is still fixed, while the second qubit is still fixed at 0. The tensor product multiplies amplitudes. It is like combining the possible motions of each coin into one larger motion. But here is something important. Not every multi-qubit state can be separated into individual qubits. For example, this state is entangled. It is not simply one qubit times another qubit. It is one shared state between two qubits. This is the mathematical version of the linked coins from our earlier lesson. Now we need one more important idea, linearity. Linearity means that a gate acts on each part of a superposition and then the results are added together. If we know what a gate does to ket0 and ket1, then we know what it does to any superposition. This is very powerful. We do not need a new rule for every possible state. Using the coin analogy, a gate changes each possible motion of the coin, then combines the results. This is also where interference comes from. When the results combine, amplitudes, qubits can add or cancel. Now we can understand quantum gates mathematically. A quantum gate is a matrix. The state is a vector, and the gate is a matrix that transforms that vector. For one qubit, the state vector has two entries. So a one-qubit gate is usually a 2x2 matrix. Quantum gates must preserve total probability. After the gate, the probabilities must still add to 1. This is why quantum gates are reversible transformations. They rotate or reflect the state without destroying its total length. Now let's look at some famous gates: X, Z, H, S, and T. The X gate is the quantum version of a NOT gate. It changes ket 0 into ket 1 and ket 1 into ket 0. Its matrix looks like this. Using the coin analogy, X is like flipping the coin to the opposite side. On the Bloch sphere, X is like rotating the state 180 degrees around the x-axis. The Z gate is different. It does not change 0 into 1. Instead, it changes the phase. Z leaves ket 0 unchanged, but it gives ket 1 a minus sign. Its matrix is 1, 0, 0, minus 1. If the qubit is clearly 0 or clearly 1, this phase may look invisible when we measure. But in a superposition, that minus sign can change how the qubit behaves after more gates. With our coin analogy, Z does not flip the coin. It changes the direction of its hidden rotation. The Hadamard gate, or H gate, is one of the most important gates in quantum computing. It turns ket 0 into ket plus, a balanced superposition. It turns ket 1 into ket minus, another balanced superposition, but with different phase. Its matrix is 1 over square root of 2 times this matrix. The Hadamard gate is not just randomness. It creates a precise superposition. Let's multiply H by ket 0. Ket 0. The result is 1 over square root of 2 root of 2. When we square the sizes, we get 1/2 and 1/2. Now apply H to ket 1. This gives us the state. Let us move to the next step. The result is 1 over square root of 2 minus 1 over square root of 2. The probabilities are still equal, but the phase is different because of the minus sign. Now watch what happens if we apply Hadamard twice. Hadamard on 0 gives plus. Hadamard on plus gives 0 again. This happens because the amplitudes combine in a way that cancels the 1 result and strengthens the 0 result. This is interference in mathematics. Amplitudes add first, then probabilities are calculated. This is one of the most important ideas in quantum computing. The S gate is a phase gate. It leaves ket 0 unchanged, but multiplies ket 1 by I. Its matrix is this. Since multiplying by I means rotating by 90 degrees, the S gate adds a quarter turn of phase. On the Bloch sphere, S rotates the state around the Z-axis. The T gate is also a phase gate, but it adds a smaller phase. Let us examine the next operation. It leaves ket 0 unchanged and multiplies ket 1 by e to the I pi over 4. Its matrix looks like this. This is a 45-degree phase rotation. You can think of S as a bigger phase turn and T as a smaller, more precise phase turn. These phase gates are very important because they change how amplitudes will interfere later. When we have many qubits, gates can still be written as matrices. If we apply a gate to one qubit inside a larger system, we use the tensor product with the identity matrix. For example, H tensor I means apply H to the first qubit and do nothing to the second qubit. Starting from 0, 0, applying H to the first qubit gives a superposition of 0, 0 and 1, 0. This is how we build larger quantum circuits from small gate operations. Some gates act on 2 qubits. These gates can create links between qubits. For example, after creating superposition with H, a 2-qubit gate can create entanglement. The result can be a state like 0, 0 plus 1, 1, 1 over square root of 2. This is the famous Bell state. It is a simple mathematical example of entanglement. Let's summarize. A 1-qubit state is alpha ket 0 plus beta ket 1. Alpha and beta are amplitudes. Their squared sizes give probabilities. The total probability must equal 1. Complex numbers give amplitudes, both size and phase. For 1 qubit, normalization and relative phase allow us to draw the state on the Bloch sphere. Many qubits are described using tensor products and many amplitudes. Gates are matrices. They transform state vectors while preserving total probability. X flips, Z changes phase, H creates superposition, S and T add controlled phase rotations. And because quantum math is linear, amplitudes can add or cancel, that is, interference. This is the mathematical engine behind quantum programming. In the next lesson, we will use these equations to understand real quantum circuits step by step.